In this lecture, we're going to do some more examples of interactions, and there's going to be some homework hints here. Um, the the previous lecture on interactions, I know, is initially confusing, but interactions are fairly simple, and you don't have to take the expected values every time. You start to just see what the interaction is doing to your model. So let's do an example. Suppose you want to find out if earnings depend on experience and education, and if the effects differ for different levels of experience and education. Okay, so this should be a clue to you whenever I say if the effects differ. Whoops, let me get the comment thing going here. If the effects differ for different levels of experience and education, or the effects depend on the levels of the other variables. This should be a clue that you want an interaction in your model. So think about a test going forward. If I say, write down a model that can test the effect of experience on in education on earnings, where the effect of experience depends on the level of education and vice versa, then you want to include the interaction. So you estimate the following model. Wages are a function of education, experience, and the interaction of the two. And the effect of education is thought to depend on the level of experience and vice versa. Your regression output is the following. So you have an intercept of 10, which means that when education is 0 and experience is 0, then you get an average of $10 per hour. Let's look at the interpretation here. So what is the marginal effect of additional experience for a person with 2 years of education and a person with 10 years of education? So first of all, what's the marginal effect of experience? Where does experience show up in this equation? It shows up here and it shows up here. So if we take the derivative of wages with respect to experience, what are we going to get? The intercept drops out because it's not multiplied by experience. Education drops out because it's not multiplied by experience. So we get, remember, these are beta 0 plus beta 1. This is beta 2, and this is beta 3. So we get beta 2, and experience is going to, we're just left with what's multiplied by experience, and then we get beta 3 times education. So that's the marginal effect of experience on wages. So let's now use this, or actually calculate this for us here. Let's now use this to find the marginal effect of additional experience for a person with 2 years of education. If I didn't tell you what education was, you couldn't calculate the marginal effect because of the marginal effect of experience depends on the level of education. So now we just plug education equals 2 into our output here. So we get beta 2 plus beta 3 times education equals 2. So this is just 3.2. We grab the value of beta 2 here, plus 0.6, the value of beta 3 times 2, because we're going with 2 years of education. So we get $4.04, 40 cents an hour. So this means an additional year of experience increases wages by $4.40 an hour on average for people with 2 years of education. How about for people with 10 years of education? Let's repeat that process, and instead of plugging in 2 for education, we'll plug in 10 here. So multiplying by 10, we get $9.20 an hour. So an additional year of experience increases wages by $9.20 an hour on average for people with 10 years of education. That's according to our regression model. So education is important according to this regression model. You get more money for your experience if you have more education. That's what this is saying, because $9.20 is greater than $4.40. Okay, what's the marginal effect of an additional year of education for a person with 15 years of experience? So now we're going to take the derivative of our equation with respect to education instead of experience. So we get 1.3, or beta 1 plus beta 3 times experience, and in this case experience is equal to 15, and so we just plug those values into this expression, and we get $10.30 an hour. So an additional year of education for a person with 15 years of experience increases wages by $10.30 an hour. Okay, suppose you estimate a regression of wages. Let's do some interpretation of the coefficients on your homework. You estimate a regression of wages on education and a dummy for male versus female, and you get the following output. So our population model would have been beta 0 plus beta 1 education plus beta 2 female, right? And there's an error term, and female equals 1 for female and 0 otherwise. And this will be two lines, one that intersects the y-axis at beta 0, female regression only, and one that intersects the y-axis at beta 0 minus beta 1, because this should actually be beta 2 because I added beta 2 there as that. And so I say minus because we get a negative coefficient for beta 2, negative 1.2 on the female. In other words, wages are lower for females according to this model, and it's going to affect the intercept. Okay. Let me just say, let's interpret all the values in this equation. Okay, so when female is equal to 0, that says that average wages are 10 because the second half of this, or second part of this equation drops out. Female is equal to 0, then we're multiplying negative 1.2 times 0. The average wage for a person with 0 years of education and female equal to 0 is just $10 per hour. And then the additional effect of, the marginal effect of an additional year of education is $3 additional per hour, but this does not depend on the female dummy. So the slope, or the relationship between education and wages, is always going to be 3. The only thing that's going to change is the intercept, the starting point. So let's graph this. So beta 0 is that this is going to be 10. This should actually be beta 2. And so this should be, I think it was negative 1.2. Let me just double check. Yeah, negative 1.2. So we're subtracting off 1.2 from 10, and that's our new intercept here of beta 0. Should be beta 0 minus beta 2. So that's how you graph the output of the model for the homework. Education on the y, or the x-axis, wages on the y-axis. This is the female line, this is the male line. The slope is still beta 1 for each of these. Okay, using regression to calculate elasticities. You're also asked to calculate an elasticity on the homework. And suppose you want to find out the elasticity of demand for gasoline. What is the elasticity of demand? It's how essentially how the quantity demanded changes when the price changes, or the percent. Definition of elasticity is actually, we'll call elasticity epsilon here. It's the percent change in Q over the percent change in P. So a 1% change in price has a X% change in, causes an X% change in quantity demanded. So to figure this out, we're going to estimate a model of the quantity of gas as a function of the price of gas. So we find that the regression output looks like this. Quantity of gas equals 30 minus 3.125 times the price of gas. So we're going to estimate the elasticity using averages. This is not the elasticity yet. We will get to calculating the elasticity in two ways here. So first, let's look at the definition of elasticity. We know it's this up here, but we can also write it this way down here. So the elasticity is the change in Q over the change in P, this part here, times P times over Q. And so what is the change in Q over the change in P? That's just beta 1 by definition of a regression model, a linear regression model. So that's great because we know what beta 1 is from our regression models, negative 3.125. we can just plug that value in here. That's what we get. And we also can get values for P and Q. So let's go to our data and get the average P and Q, and it turns out the average P is $3.2 per gallon and the average Q is 50, let's say. And then we plug those values in and we get negative 3.125 times 3.2 over 50, and we get a value of negative 0.2. Or this says a 1% change in the price of gas causes a 20% decline in the quantity of gas demanded. We could do it a different way. Recall from lecture 4 that if we log both variables, then the interpretation of the coefficient beta 1 is actually a percent change. So if we logged both variables, so we're literally going to our data set, our spreadsheet. If we have Q, why do I keep screwing this up? If we have Q gas and P gas in our data set, and we maybe have like 50, 51, 52, and then the prices are $2.90 and $3.10 and $4.20, whatever. Log Q gas is just going to be log 50, log 51, log 52. I don't know what those are off the top of my head, but your spreadsheet could do this. And then log P gas, it's just going to be log 2.9, log 3.1, and log 4.2. And what this really does is just turns it into proportions. And so if we regress log Q gas on log P gas, like we've written here, we find that log Q gas is equal to 2.4 minus 0.23 log P gas. Then the elasticity is simply the coefficient, negative 0.23. So the interpretation of the beta 1 coefficient in a model with both variables logged is the percent change in X causes a beta 1% change in Y. In this case, it's a percent change in P causing a beta 1% change in Q. So it's negative 0.2 or 23%. So that's close. So the lesson here is that we can estimate elasticities two ways. We can do it by logging both variables, or we can do it by using this formula here. We're going to get slightly different answers, but that's simply because they're different methods. We're multiplying by P over Q here. We're not here, but they're pretty close. That's the point.